Good evening all, and welcome to this evening's event. Tonight we're looking at a topic from the VCE Specialist series. Now this series is looking at the revisions to the study design. We're running this for methods as well as special. And tonight's topic is matrix transformations. So we're going to be shot back into the matrix. And that might sound a little scary, but be reassured, we are in expert hands. We have Mr. Peter Fox as our presenter, taking us back into the matrix, and I'm sure he will guide us very carefully through there. So you see Peter's face on the screen now. Good evening, Peter.
Good evening, Brian.
And you can see there that Peter actually manages the digital content. That means the website and other support materials, such as the videos that go to YouTube from TI Australia. He's been teaching for, you can see there, lots of time, and also working at the various universities in Melbourne. And I have seen Peter's capable presentations at a range of conferences, both in Australia and overseas. My name's Brian Lannon. I'll be your host. I'm in the background. So if you have any questions, please type them in. Send the questions to everyone so we can all see what's going on. And if I can, I will answer it for you. Otherwise, I may interrupt Peter and draw his attention to it. So you see the chat bubble down in the bottom right. So just hit your questions in there. So without further ado, I shall hand over to Peter.
Thank you, Brian. I thought what we'd do for this evening's webinar is, because matrix transformations were actually included in the mathematical methods study design, I thought we'd have a look at some of the similarities. So we'll start with going through the dot points that are included in the study design under the heading of specialist mathematics. One of the dot points being points in the plane coordinates, and their representation as 2x1 matrices or column vectors, and it does actually stipulate column vectors, so it's telling us the format that we're expecting to see. So really simply, if you haven't taught methods with the transformations in it, it's basically just saying if you have a point, say 3, 4, then expect it to be represented like 3, 4. I don't think specialist teachers will be too concerned about that one. We're seeing that with vectors in other forms anyway. So that's what it said in the mathematical method study design. It looks like a copy and paste, pretty much the same. So moving right along, let's have a look at another one of the dot points and a quick interpretation. So translations of the plane. So we can see here that this one is literally just translation in the X or Y direction. So essentially we've got some sort of a function, and we could use a matrix to slide it to the right or left or up and down. Did that appear in the methods course? Well, kind of. Not actually as a dot point, but generally described as a transformation, so holistically, which could include translations, obviously. Interestingly enough, in the methods study design from 2016 to 21, it specified the types of functions we would expect: sine, cosine, tan, exponentials, and simple by hand cases. So it was included, nothing new. And another one, linear transformations. So this time you'll notice we can have ax plus by, cx plus dy, mapping the plane onto itself, rotations about the origin, and reflection in a line through the origin, so very specific there. Let's have a look what that might look like. We might get the parabola and rotate it. And here's what it said in the method study design from 2016 to 21. Another case of copy and paste by the looks of that. So not much changes in that part. So is there anything new? Let's have a look. The effect of translation, linear transformations, inverse transformations, and I'll demonstrate how that might have been useful in some past exam questions, students thinking of it in that way. And you notice here it says points, lines, and shapes. and graphs of functions and relations. So it's just describing all of the things that were covered in methods, but it's also pointing out that you could do shapes, and we're going to use those later on because I think they're actually a really powerful way for students to learn, because you can also do transformations of shapes in, say, year 10 or year 9 as part of geometry. I think it's really handy to do it that way, in fact, to start with the geometry, that is. So we could have a shape and transform that. Any other dot points? There's one more. Invariance of properties under transformation. So you saw, say, for example, that rotation, the origin, or the turning point rather, on that parabola would have been invariant. And linear transformations of the area bounded by the region. The determinant, what role does the determinant play, and how does that impact the area? We'll have a look at that. Alrighty. Because this has been covered in methods, I thought probably worthwhile having a look at past methods exam type questions to see the sorts of things that might be asked on the exam going forward. Because there were so many dot points in common, it would make sense that some of these questions would be revisited. So here's one from the Methods 2020 Exam 2, multiple choice. They specified they could be a graph of cos x, so this is quite within the realms of what we would have expected. You'll notice in this one, zeros on the diagonal, so simple dilations in the x and y direction, a simple translation. So how did students, oh dear, only 26% of students got that question correct. That wouldn't be so bad if it was a short answer question, but given it's multiple choice, just pure guesswork could have got us to 20%, right?
Well,
so that's a
guesswork
concern.
20. Yeah, that's right.
Yeah.
Multiple guess,
in fact,
Peter.
I think some went for option C. You know the old rule, if you don't know what it is, go option C. 38% jumped on C.
Yep.
All right, well, maybe we'll have a look at a different year. Here we go. Here's one from 2018. Same sort of thing. We've got some a function. This one's interesting because it's talking about a probability density function that may have put students off. I don't think there was anything necessarily inclusive about that, just that we have f dashed of 0 equals 4, g dashed of 0 equals -1. So there's a few extra bits. And 20%. I think, Brian, we're at just straight guessing now, aren't we?
There we go.
Fact, if you look at the distribution of selections for A, B, C, D, and E, there was something about E that disturbed students, but otherwise 20, 26, 21, 21, that's just pure guesswork, I think. Most students pack that in, and I fear that just saying there was a probability density function probably put students off. And you can see here that there's no reference to the probability density function at all in the examiner's comments. Yeah. Just the transformations part.
Peter, I don't know if you noticed, we did have a question in the background there, someone asking where they're mapping. You can see there we're mapping from R to R, but in an earlier question, it was R squared to R squared. Somebody else, another participant has answered it.
Very nice.
And yeah, indicating that it's plane, a two-dimensional plane to a two-dimensional plane.
Mm-hmm. And interestingly, I'll give a heads up. If you want to get a really good, deep understanding, and where I pinch some of these ideas from, is a YouTube person called Grant Sanderson. And he does the transformations in the plane and then talks about what happens if we do it in 3 dimensions. Pretty sure the specialist course is not going there. But when you're talking about shapes, if you're talking about solids, that's okay. But it also helps bring about why we bother with all of this stuff. Kids might be sort of saying, why are we doing all this thing? You know, well, what's the point of it? It's in computer graphics, enormously so. And Grant Sanderson does some really good videos, some good visuals that you don't have to do a lot of maths to get into it. Just sit there and understand and watch what he's doing. It's really cool. So here's one from 2016, Exam 2. This is another one where we see like an integral in this case. So it is actually got areas in it, even though it wasn't specified in the study design previously. And this time we're actually worse than guessing. That's really sad. 17% got it right. In fact, if you'd guessed, you'd had a slightly better chance of getting it right. We should probably do some statistics and check to see whether or not that's an outlier at 17. Certainly the 30 is, I would have thought, given the number of students that would have been responding to the question. So look, the past exams are good spaces to look for these questions. However, I think it's clear that we need to give the students a better understanding of the concept, because if you look at the algebra, it's not that complicated in most questions, and most of it's numerical. So our students should be going better. I think they're struggling with the concept, so we're going to have a bit of a deep dive on that. Now, this one was from 2019, and this will, I guess, hone in on the point that I'm trying to make. When we see 57% of students got this correct, that's very different than all the other exams that we've been seeing. So let's have a look. Why did 57% get this correct when we've been hovering around guessing? And it's pretty clear there was about 10% guessing across the board here, but 57 here. If we have a look, point AB is transformed by these matrices. The image of AB is 0, 0, then AB is equal to, and the students had to choose which one that might be. So what I'm going to do is demonstrate how that might have been done by students. Now, they may have done it by hand, in which case, and I tend to use the notation x prime, y primed as being our transform points. So this is basically a duplication of what's written in the question, only I've used x primed and y primed. So let's just transpose this a little bit using our matrices. So all I've done is just shifted them across, because we're actually told that the image is at 0, 0, and we have to work out where the original point was, this AB, or in our thing here now, XY. So essentially, what students could have done on their calculator is that. So I've put in my 0, 0 as the transform point. So I'm using my inverse matrices to do this. And we get 1, negative 1, which indeed was the correct answer. So I suspect that's why we see such a big change in the outcome here, and in a good way. So I figured that would be a good place to start with students, is starting with points and numbers and matrices. Now, there's some cool features on the CX2 that are going to allow you to do this. You can still do it on the CX. So if your students have got the original calculator, the CX, they can still do this, but they have to do it in a slightly different way. I will demonstrate both options. One's a little bit harder than the other, so we've kind of made it easier, this point by coordinates. And there's a really cool and simple to use shortcut here, and it's just press P. So when you're in the graphs application, you press P, you'll see that little menu pop up. So let's have a look at what that looks like. Oops, went one too far. So I'm going to insert a graphs application here. And if I just press P, it's going in there. So I'll escape and press P, and there's my menu. So I can choose point. Now, previously, or if you're on the CX, not the CXCAS, geometry, point, and just put point. You can see now it has this shortcut P. So I'll go back, I'll press P. Now, when you do that, I've got the grid showing in the background. My idea is that you try and keep things as simple as possible. So if you're not sure where the grid is, you go into menu, and we can do view and grid and no grid. I've got dot grid on. It's just because that's what I want it to be. You could choose line grid, but in this case, dot grid. The reason, of course, why it's grayed out is because it's already on. And the grid spacing is based on whatever your x-axis scale is. So if I change that to a 2, you'll see the grid just spans out. So I digress. I'm going to put point on the grid. And that's it. And I'll right click and get its coordinates. So here we have the coordinates of that point. Now the reason why I've got the grid, look at that, the coordinates are really simple. If they're decimal values, it's just going to be distracting. For the purposes of this, as I said, I'm trying to keep things as simple as possible for the students. Now, the next bit is I want to store these coordinates somewhere. So I'm going to right click. So if the student's using the calculator, they just put the mouse over them, press Control and Menu. And it allows me to store the abscissa or the X value. And I'm going to put that in something called X1. Now, this might seem a little trivial, but I mean, you can put a normal 1 next to it. I just don't like the notation. So I'm going to have an X with a little subscript 1. And if I hover back over it, you can see it's bold now. It tells me that the abscissa is connected to X1. I'm going to do the same for the Y value. And when you've done this a couple of times, it actually becomes pretty quick. So I just type in Y and I want a 1 there. So I've got this X1, Y1. So what? Well, now I'm going to do P. And this time I'm choosing the second option, point by coordinates. And you can see how messy and horrible those coordinates are. I've got nothing against negative 6.29, whatever the rest of that is, except that it's distracting. I'd rather see an integer value. But what I'm actually going to do is say, I want that to follow a formula. I want it to follow a rule. What rule do I want it to follow? Well, I want it to be equal to X1. So I'm just going to do my little subscript, plus 2. The Y value, I'm going to make that Y, let me think, minus 3. Why not? Why not? So subscript 1, and I can just arrow out of it. You see the cursor becomes taller. Y1 minus 3, press enter, and I'm done. Now I can press escape. Now, here's the cool bit. I'm just going to drag those coordinates up there. And it tells you X1 plus 2, Y1 minus 3. So now let's move this point. And we can see that our second point is kind of following along. So it's 2 units to the right. Well, without being too stupid about it, well, we said to add 2 to it. And it's 3 units down. Well, we said take 3 units off this Y value. So it's just following along exactly how we've described here. So after doing all that marvelous work, I'm actually going to delete that point. Interestingly enough, it's still saying I'm going to follow X1 plus 2 because even though I deleted a point, it's just holding on to its memory. So now I'm going to put a function in. I'm just going to make that X squared. I'm not very exciting with my functions. I know I could have done something really cool there, but I've just left it as Y equals X squared. And I'm going to press P and choose option 1. And when I hover over the graph, it's going to say point on. You can see the graph has dotted and it's giving me the option point on, and I'm done. Now, I'll have to put up with these horrible decimal values this time, but I'm going to do the same as I did before. I can now right-click on that value and say store that in X1. Notice this one updated. Kind of cool. And I will store that one in, and I think you probably know where we're heading with this already. I'm going to store that one in Y1, and I'm done. So now, as I move this point, it would appear that our translated point is kind of following the path of a parabola. Who would have thought? So I could, and there's a couple of ways I can do this. I can say menu, geometry, trace. I want trace, geometry, no, try that again. Take 2, menu, trace, and we'll do a geometry trace. So we click on our point that's moving around, and then we drag this one, and we see that it's plotting the path. Now at this point here, students could figure out the equation to this because they know what the actual translations are. But if we do it in matrix terminology, or at the very least, write down that this point here is equal to, let me just jump off there, is equal to x1 plus 2. So we can say x primed is equal to x1 plus 2. And y primed is equal to y minus 3, or y1 minus 3 in this case. And then have the students algebraically determine the equation to this graph. So let's return back to the slides. Our matrix transformation, as I said, I've got x primed. It can be A, B, C, D. So what if I did something like that? What would that look like? So if we multiply those matrices out, we would get x primed equals 2x and y primed equals y. So in other words, we want to just double the x value. So let's go back and do that. So we can edit these things. So I'm going to delete that one and put a 2 here. So we said we're going to double whatever the x value is. And for the y value, it's just going to be the same. We're not going to do anything to it. Now the other thing is, you can see it's left this trail behind. To clear that off, trace, erase. So now, as I move this around, and these are the ones the students often get wrong. All right. So we can see it looks, as the students would say, wider. Well, it's been dilated. The graph is infinitely wide, by the way. So let's go back. This seems to dilate the function. Well, that bit's a no-brainer. X primed equals 2x. I'll just multiply those matrices out. So what do I do with this? And this is where students often get stuck. Well, my graph that I'm trying to figure out the equation to, this one over here, in fact, I'm going to change the color of that point just so I can refer to it a bit better. The red point, that's our translated point. That's our x primed, y primed thing. I want a rule that relates y primed and x primed. I don't have one. But I do have a rule that relates x and y, our original function. So the rule that relates x and y is y equals x squared. So I could transpose this and substitute, because I'm trying to find an equation for x primed and y primed. This is what we're trying to get across to students. So, pretty simple algebra. Like I said, I don't think the kids are falling apart on the algebra. In pretty much all of those past exam questions, the algebra is not complicated. The concept is where they're struggling, I believe. So now we can just do a straight substitution. I know what x is. I can substitute it in there. And it's a no-brainer. We can already see we're going to get x primed squared, if you like, on 4, or just dump the whole thing in some parentheses. And the y just does a straight swap because I didn't do anything to the y's. So we get this. And now that we've got this rule to graph it, we can just drop the primes on there. And I could just write it as x squared on 4. And that should be our rule. So let's try it. X squared over 4. And our point is sitting on the function. So we can see, did we get it right? And this is one of the other advantages of doing this. I know it seems convoluted, but clearly the kids are pretty much guessing. They're not getting the concept. Well, at least the method students weren't. And when we see 20%, a proportion of those are also our specialist students, obviously. And I don't think they're getting it either. So now the students have got a lovely way of checking, is it right? Is my equation right? And when I had it before, if you do those transformations there, then and you saw the way the graph was translated, and I think you'll find students tend to say, oh, you just do the opposite of whatever's in the bracket. So an x minus 2, that means it moves in the positive direction. Why? Why does it do that? And when the students do this, they realize why. And this scale factor of a 2 that we had before, I'll just reverse back up here. Why is that, when it's multiplying the x by 2, why is it doing that? And yet when we do it here, we see that x value is double that one. It's exactly what we said it would do using the matrix. We doubled it. And that's the effect that it has. It pushed it over here. So using these discrete values, I think, helps students, because when they're dealing with what I think there's some students, some Masters of Education students in Queensland doing a presentation on this very concept of working with what we call a wireframe, so a line, a continuous thing, compared to working with discrete values. So I'm thinking that might be where the students, the methods students have been going wrong, and I'm sure that that group in Queensland will reiterate what we're saying here. So that's that one. Let's just zoom through those. All right, so what happens, where are we? What happens with this one? That's kind of messy, isn't it? We've got a 2 and a 1 and a -1 and a 1, and it's like, whoa. How does that work? Well, this is where we can have the calculator do some algebra for us. So we'll give that a crack. Where are we? There we are. So I'm going to drop in a new problem, document, insert, problem. That means that my x1s and y1s that I attached to that other thing are now gone. They're not recognized here. You can see it's clear. And if I go back here, oops, I've got some variables, f1, f2, x1, and y1. All right, so I should have written the question down. I think I've got it here. So what we've got is, and I'm going to show you some quick ways of doing matrices. So we can do a column matrix here, 2 by 1. And we can call this, now here's the catch, you can't really call it x prime. That's an annoyance because of the fact that the prime is coming up as a derivative. So I'm going to do my little sub-value there, and then another one. Didn't mean to press enter. Now, this may seem strange as I'm pressing an equal sign here, but hopefully that will make sense in a moment. So the transformation that we had, now I'm going to show you a different way to do this, particularly handy if you're doing on a computer. So the matrix that we had was 2, 1, and it was a -1 and a 1. So the comma separates elements in a row and the semicolon separates them in, says false, false, because obviously it's the wrong dimensions, but you can see how we can create a matrix. So if I want to do a column matrix like we've got here, we have x, semicolon, oops, y, and oops, what's it missing? Doesn't, oh, it thinks it's missing a bracket. Let's go back out of there. I'm going to do it in this way. X, Y. Don't think it liked the way I pressed enter. So now you can see why. Let's just get rid of that one and that one. Now you can see why I've put the equal sign in here, because now I've got this x1 equals 2x plus y and y1 equals y minus x. So this is like my x primed and y primed here. So the challenge that we had before, and I'm not going to do it here because we'll run out of time for all of the other stuff that I want to cover, but the challenge the students have now, and this one has got a bit more algebra involved, nothing, and the basic linear things that the kids are working with, because they have to get x by itself and y by itself. So there is a bit of a challenge here for the students. But the question is, could we still do this, and what would it look like? So if we had, let's say, the graph that we had before, could we do it? Could we use that thing that I've set up here, that this thing that looked quite simple and trivial to set up? Of course I can. So now I know that I've got to do 2 lots of the x and y, I'll see if I can remember that. Actually, I'm going to write it down. 2 lots of the x plus a y, and the y transformation is y minus x. So let's see what that looks like when I go back here. So this is my transformation here, and I wrote it down. It says 2 lots of the x plus y, and remembering it's y1. So I'll do my little sub value there. And the point's moved all the way over here. And this one says I need to be y1 minus x1. We're at x1. Pretty sure that's not the graph there, so how about we delete him? So now let's have a look what the graph looks like. Oh dear. Let's do a trace. Menu, trace, geometry trace, and now drag him around. It still looks kind of like parabola-ish. It looks a bit like it could be a rotation, but there's probably a dilation in there because, as the students would say, it looks wider. So all the students need to do now is exactly the same algebra as we're doing before. We need to get x by itself in terms of y primed and y by itself in terms of y primed, so we can substitute it into the rule that we do know between y and x, being y equals x squared. Now, if the students do that successfully, they will see that it's a relation. We can see it's a relation, so I'll press delete and option number 6, and here's what I prepared earlier. It comes out like this: x squared minus 2 times x times y minus 3 times x plus y squared. You can see it gets a bit ugly. Minus 6y equals 0. And there's our graph. I'm going to hide or erase the trace, actually. Trace. Erase geometry trace. I feel like I should make it red. So there's my new function as a result of, let's go back to the transformation. As a result of this matrix transformation, I get some rule, g of x and y, and there it is. And I can check to make sure I've got the rule correct. My transformed or translated point, transformed, is correct. And there's the transformations in there that I got from the matrix. 2x plus y and y minus x. That's what it told me over here. So all I've done is obey that, done the algebra, and now I can check it. And I think that level, starting with a point, and in fact, if I move this, I'll try and get it to a nice whole number. Get it as close to 1 as possible. We won't get it exactly. Pretty close, that'll do. Pretend that 1 there doesn't exist, all right? So it says 2 lots of x plus y. Yes, I've got 2 lots of x plus y. Yes, that is correct. And I've got a y minus an x. So yes, I get a 0. So I can check individual points as well. But now hopefully you can see why I was so particular about landing it on integer values before, because now there's a bit of annoying arithmetic that I've got to do. And it's not obvious now that that's 2 times that plus that, and that is that one minus that one. It's not as obvious. We stick to integer values and it becomes easy. All right, so that's a little bit of our transformations and the sorts of ways you can do that using points on the plane. Let's send him away, and let's go back to one of the things that we've got to cover. We've got to cover area, and that's one that hasn't been talked about yet. And also the effect of a translation when it comes to, where was it? I saw it in here somewhere. Inverse. There's a nice one with inverses that could have picked up, and we have to talk about the determinant as well and how that affects the area. So let's have a look at that one. How does this determinant affect the area? Now remember it said shapes, so I've made this really cool document which I'll share with folks. because it does take a little bit of time and effort to make it, but you've already learnt the skills by which you can make this document. So let's go back to Nspire, and here it is here. So what I've done, if I hover over that one, you can see that this point is linked to x1, this one's linked to y1, this one's linked to x2 and y2, x3, you can figure out the rest. I've drawn them as shapes, so I've done 4 points, and then I've just drawn a shape over the top. So it was menu and geometry and shapes, and I just did a polygon to sit over the top of our 4 points. So I just clicked on it and it creates a polygon, and I coloured it in. No crayons involved here, it was digital colouring. So where do these points come from? You can see that the x value is being doubled, the y value is being doubled in every single one. Well, that's because in the background, in the notes application, and we've talked about these plenty of times, insert a math box, I've got this transformation matrix, which I've called 2, 0, 0, 2, stored it as t, and then I said, you know what, I'm going to have another matrix, which is just the product of our transformation, x1, y1, so it gives me the new points under the transformation. So in other words, if I look at x1, I'm guessing it's 1, and y1 is probably 1, because when I multiply that out, let's have a look, x1 is 1, y1 is 1. And I just did that for, and then this is a bit tricky, you may not have seen this before, if you want to reference a specific value in that matrix, you just tell it the row and column that it's located in. So we've got this in row 2, column 1 to get that 2. And then I just did that for each of the points. So there's a little bit going on there, and that's it. That's the whole kit and caboodle. But you can have this one because I'm now interested in how the transformations affect the area. So we can see in this case, the area here of this transform shape is 4 times the size of the one that we got. Now this point here is kind of hidden underneath, so you press tab and you'll get back to your green point. So if they sit on top of one another, you press the tab key to access the one that sits underneath. They're like layers. Onions have layers. Sorry, I digress. So we can see that no matter what I'm doing with this shape, it just continues to be 4 times the size, and you can see these points moving accordingly. And again, going back to that idea of the discrete nature of these points, I've put them on the grid so we can see, yes, all I'm doing is doubling these coordinates. That's what that matrix does. What if I don't double? What if I make it 1? Well, now I've got this weird shape. It's kind of stretched in one direction and not the other. But notice what's happened to the area. Now the area is only double. Let's check these out. The x values unchanged, the y values are doubled. Of course they are. Look, think of the x, y here, 1 lot of x, no y, no lots of x, 2 lots of y. Of course it's doubled in the y direction. I'm doubling all the y values. Look at me here, that's exactly what we're doing. So what if I make that a 2 and that a 1? It's good that students ask the what if questions, and of course it's now stretched it in this direction. These are the concepts we want the kids to have. And you can see the shape, the gradients. We can talk about things that do change, like the slope of that line is changing. What about, let's do something really wacky. Let's put a 1 in there. And we'll put a 2 in here. Ooh, look, it's a weird shape now. It doesn't quite look the same. It kind of, I'm going to say almost like it's been stretched out on the diagonal. Look at that diagonal. It's much bigger than what it was before. And I wonder if we could get that diagonal almost the same. You know, it's like, But have a look at the area. That's a weird one there. Let's see if we can get it. Oh, look, it's 4 times the area. Let's go back here. I'm going to take that 1 out, and I'm going to change it back to a 0. I wonder if that changes it. Look, oh, look, still 4 times the area. What about if I put the 1 down here? What's going to happen? Nope, still 4 times the area. So the students can start to hypothesize. Now, here's the problem. If I go 3, you'll find that some of these points might disappear off the screen. So you'll need to make sure this shape is fairly small if you start doing big ones. So that's now 6 times. And I'm going to guess if I turn that back to a 0, it's still 6 times. I'm going to change this to a 1 and that to a 1. Let's see if it's still 6 times. Nope, 5 times. Now, there are various proofs out there on the web as to the relationship, why the relationship is this, but quite simply, and some of you may have guessed already, if you calculate the determinant here, so 3 2s are 6, minus 1 gives us 5, and look at that, it's 5 times the area. So therefore, if I change that to a 2, let's make a prediction. So 6 minus 2, it should be 4 times the area. Look at that. Look at the weird shape we're getting. So that should make students start to think now. So I know how to make it 2, 3, or 4. You could even ask them, you know, what values could you put in here to make the area 3 times as big, or 2.5 times as big, or half the size? But here's an interesting one. What if I make that let's make it a 3. So 3, 3, 2, 2. So 3 2s are 6. Oh dear. The determinant's going to be 0. How is it possible to have 0 times the area? Oh, well, look at that. We started with a 2-dimensional shape, and we've ended up with something that is 1-dimensional. It has no area. So if the determinant is equal to 0, it actually changes the dimension of our shape from 2D down to 1-dimensional. You could then ask the students to ponder, so if this was a 3D shape and the determinant was 0, would that mean it's a 2D shape, no volume, or would it have to be a 1D? So let's get away from that because I need a shape back. There we go. Now, that one is, oh, look at that. 3 times 1, 3, minus 6. But that makes it what? Minus 3. So our area is 3 times. So what's with the minus? Does that mean we do an absolute value? Because that's sitting all under there, I'm actually going to swap them back. I'm going to make them a bit smaller. I'm going to make that one 2. So 2, 6. Let's change that to a 2 as well. So our discriminant is still negative. So we've got 2 minus 4 minus 2. So our area is twice the size. So do we just ignore the negative sign? Now, again, Grant Sanderson has a wonderful explanation of this. His is a lovely 3D sort of an animation that he does. But let's have a look at the, I've colored these for a reason. So if we have a look, it goes red, blue, green, orange as I go around clockwise. Red, but oh, it's back to front. Red, blue, red, it's going, this one if I'm going counterclockwise, well, let's go clockwise, maybe it works. Red, orange, green, red, nope. So essentially what it means is the shape is flipped. So if we're thinking just focusing on the area, then you take the absolute value of the discriminant. But if you want to know whether the shape's actually been flipped over, the negative sign in the discriminant will tell us that it's been flipped. So I think that's a handy little document, and we'll have that up for people to download so that the students can play with that. You can see there's very little challenge in the mathematics there for students. So what? Is that really going to help them answer these exam questions? I believe it will. Here's one that students did poorly on. Well, they did poorly on a lot of them. So if we look at the transformation, that's just exactly what we've got written there. Nothing exciting. So x primed, if we multiply this through, we get negative x and no y's and plus a 0. So we just got x primed equals negative x. And our y primed is just the no x's, 3 y's, yep, tick that box, plus the 5, got it. Now remembering, we have a relationship. Well, we have f of x, y equals f of x. So we have a rule that relates, and we know some stuff about that rule. So it would be handy if we had y in terms of y primed and x in terms of x prime. So we can do that. That's a pretty simple one. Like I said, the algebra is not complicated. So now we've got y in terms of y primed and x. So we're saying that f of x, that's what y is. We know that y equals f of x, and here's an x. So we can already see if we substitute that in, we're going to get a negative x in here. And think about what that's doing to the terminals here. So we can write this step down. That's just substituting in my y is equal to this, and I'm substituting in my negative x for the x value. And the kids end up with this, that if we want to find the integral between 0 and -3 in that order, then it's just 3 times, well, I've got it back up here, 3 times the integral. We swap because of the negative sign, and then we've got to integrate the 5, which became 5x, from 3 to 0, and we get 15 plus, what's that work out, 15, 30, so it's E. And only 20-something% of students got that correct. So we're almost out of time, Brian. We said about 45 minutes. Do we have any other questions from participants? Let's have a look. Can you explain the ask? Yep, people have done that one. 2D plane, yes. They didn't have the foundational understanding of matrices. Yes, I believe that could be true.
A comment on the syllabus construction there and why we were getting those results. Yeah. But I'm a big fan of what you've done there tonight, Peter. Anything for me that has multiple representations, to me, that's the whole purpose of this stuff, or the value of it, to build that understanding.
Someone made a comment about the implicit stuff, so let me just jump back to that one. And
that was when you did.
So you could see, say, for example, so we could do the derivative of that and say if we do the transformation, I mean, hopefully you can see it straight away. It's not going to be right. If we transform that function into this one using that transformation matrix that we had here, does the derivative transform in the same way? Well, hopefully people can see, well, that the derivative of our x squared function is just going to be 2x, but this is not going to be the same transformation at all. So we can do implicit differentiation across that to see what happens, but we can't just translate the derivative function because that's going to end up like a linear function as well. So a bit more work to do there, but students can, and I can imagine, as someone's alluded to, that maybe we're going to do some graphs of derivatives in there as well, because if we're going to end up with implicit functions, we can see that probably implicit
implicit relation. Yeah, implicit relation, you had to set that up using the relations rather than your original parabola, of course, was set up as a function.
Yes, that's correct.
Yeah, which is another really handy feature there. So it was good. As you can see, we had quite a few online tonight. And if I could add to your puns, the way that you have animated the matrices is a real animatrix.
Very nice.
Yes, but particularly, I think the strength there, of course, is the link between the the matrices and matrix algebra and the geometric visuals. As they say, a picture's worth 1,000 words.
And
being able to tweak it, being able to ask those what if questions, as you say, and it gives real meaning to what's happening with the the determinant of the matrix there.
Yeah, and the bits that I didn't include here, because I don't, as I keep saying, most of the algebra that you're going to cover in here is not complicated. I believe it is the concept. So students could solve this, and then they could have done solve. I think that's just been somewhat lazy, though.
Yeah. That's exam question stuff.
Saying solve it for y and doing some substitutions. That's kind of trivial. That's why I kind of just copied and pasted that equation in, because I didn't want to go through all of the algebra. It's actually easy to do it by hand compared to what it is on the calculator, because you're copying and pasting everywhere. It's crazy. Get them to do that algebra by hand. They don't need a calculator for that. But I think they do. I think this is an example of where we're using the calculator to develop the concept, because I don't think there's much button pressing they're going to do other than that one. I think, what was it, 2019, where it was literally just, and even then, I'm sorry, if they're doing that, I guess you could do the inverse matrix, but it was a fairly trivial example, right? To do that one to work out the point. Yeah, maybe they did. 56% of students got it right, so we're good to go.
Well, of course, your starting point was the examiners' reports, and what you've illustrated tonight, of course, isn't the way that you would go about such questions in an exam.
No, that's right.
You just do it the quickest way you can, such as what's on the screen now. But you demonstrated from the data from the examiner's report where the problem is that the students don't have the underlying understanding.
That's it.
And of course, all of the geometric linkings that you demonstrated. That's what's going to be very valuable in the classroom.
Yeah, and I really do encourage people to have a look. If you get onto YouTube and look at Grant Sanderson, linear algebra and matrices, he covers it really well. I think there's even the potential for some students to watch some of those videos. Don't let them wander down the path because there's too many distractions on YouTube. Maybe even show just a section of it in your lesson. Pick out the part that you want, because his visuals are really powerful, because it's a concept we want these kids to get, and then throw in some of these sorts of activities that we've been doing here. And I think students will go a lot better on those exam questions.
Okay. Yep. Yeah, I've just typed that name into the chat there, in case people want to follow that one and type it into YouTube. Just a reminder, with lots of thank yous coming in at the moment as we close down. Just a reminder, if you're following the specialist series for VCE study design review, we have another one next Wednesday, 19th of October. That's on lines and planes in 3 dimensions. On the 25th of October, which I think is a Tuesday, sequences and series. And then on the 27th, that would then be a Thursday, arc length and surface areas of solids of revolution. If you scroll back through the chat, or just go to I've put the link to registering for further webinars, or of course just go to the TI website and register there. So I will add my thanks to all the ones that are being typed in. Peter, very enlightening webinar this evening. I will close the event now, and of course you can access the recording at a later time from either the TI Australia webpage or our YouTube channel.
Thank you, Brian.
Thank you indeed. Good evening to all.